I did a maths degree, but I wouldn't call myself a mathematician, so this is going to be a lot different presentation. This is going to be on the carbon cycle and climate impacts on the carbon cycle. And I realise that most people in the room probably aren't carbon cycle scientists, so I'm going to start kind of big picture, kind of setting the scene on kind of the global carbon budget, which is what I spend a lot of time working on, and how Jules, which is obviously in the ad trees, kind of fits into this global carbon budget and kind of the links between these two projects, and then go on to talk about climate risks for ad trees. Okay, yeah, so start off with intro to Jules and the GCB, then talk about how has the UK carbon cycle actually changed in recent decades and kind of what's the climate impact we've seen. I'm going to talk about advancements with Jules specifically that allows us to kind of actually make possible the ad trees tool, and then look at climate risk in the UK, and then talk at the end a bit about wind damage using the forest scales model from forest research. Okay, so what is the global carbon budget to start with? So the global carbon budget basically tries to track all sources and sinks of carbon across the globe. So on the left-hand side, you've got sources of carbon. So you've got fossil fuel emissions, deforestation. Vast majority is fossil fuel emissions, at 90%, as we all know. And then this carbon has to go somewhere. So it either stays in the atmosphere, and about 50% of our emissions stay in the atmosphere, and the other 50% either absorbed by the land or absorbed by the ocean. And what my research focuses on is this kind of middle component, this land component, which absorbs 30% of our fossil fuel emissions. So the increase in CO2 in the atmosphere is directly driving the carbon sink in the land. So to estimate that 30% land sink, we use DGVMs or vegetation models. Jules is one of these models. So this is a basic schematic which I made, which outlines the Jules model or any DGVM. So on the left-hand side, you've got input data. So you have climate forcing, soil ancillaries, elevation, and land cover. So we can take satellite products of different land cover, and we force the model. This in the middle column is basically what Jules calculates. So we've got physics. So you have energy transfer, momentum transfer, water fluxes. You have leaf level processes from photosynthesis using smarter conductance, evapotranspiration, and then the vegetation dynamics. So how do the carbon stocks and the trees actually grow and compete with each other? And then at the end, we get our carbon, nitrogen, phosphorus outputs, which we care about. So, as I said, so if you look at how kind of the historical trends in the global carbon cycle, so we've got atmospheric CO2 has been increasing over time, temperatures have been increasing, that's the red curve on the bottom left, and we've got high variability in precipitation, and we've had land use change as well. So we've had large-scale deforestation, increase in croplands, increase in pastures, and this is what the kind of global sum comes to. So this is the net land flux, a global scale. Take all the processes together, what is the land doing over the last 60 years? And we've seen there's an increase in the land carbon sink. And there's a huge variability. But what these models allow us to do, so Jules is one of these tiny, the thin green lines, and we have 19 of the models, and we kind of take the ensemble mean. But what the models allow us to do is kind of capture the processes. So we can ask, why is the land sink increasing? And the DGVM suggests that this is actually driven by CO2 fertilization along with nitrogen deposition. So to increase CO2, the plants love that, especially in the models. They just keep growing because there's more CO2 in the atmosphere. On average, land use change, mainly tropical deforestation, is causing net losses of carbon. That's the grey line. So this y-axis is kind of the change in the carbon sink over time. And then you have this huge year-to-year variability because of climate variability. So that's basically El Nino cycles. When we have a positive El Nino, we get drier, warmer over land, we get much more loss to the atmosphere. So I guess the point I want to make here is, obviously in Add Trees, we talk a lot about forest management. You know, we're seeing these curves starting at 0 and sea veg is growing up to some asymptote. But a big part of the carbon sink is the CO2 fertilization. So it's not just forest regrowth in its entirety, it's the conditions where the forest regrowth is happening, so CO2 and climate change. So if we zoom into the UK, this blue bar is the net UK carbon sink according to the model, so Jules is one of these, and we see that it's a small net carbon sink in general, so positive values of the sink, but you can see this large annual variability. So some years we're having gains, some years we're having losses because of warmer temperatures or dry or whatever it is. And then kind of as a reality check, I plotted on that red curve there, which is just above 0. And this is taken from the UK's National Greenhouse Gas Inventory, which they report to the UNFCCC. as part of the kind of climate mitigation process. And we see that we match pretty well, which is kind of a nice thing to do. So as I said before, yeah, so it's climate variability and trends are important. So it's not just a forest management issue. Again, we can do the process attribution. So what is driving the UK carbon sink? According to the models, the blue line here, which it shows that it's CO2 and nitrogen deposition. Land use is actually causing a lot of carbon in the UK, but this is predominantly from peatland drainage. So there's a huge impact of peatlands on the carbon sink in the UK. There'll be some reforestation happening, but there's not really that much happening right now. And then climate change over time is actually causing net losses of carbon. So we're getting warmer, drier, whatever it is, it's causing decreases in carbon uptake, which is something we need to kind of be aware of. And an important point here is that the DGVMs, so this is nice hearing Susie's talk earlier, the DGVMs aren't very good at forest management. So we can use them to see what happens if we plant trees, and we can see the models grow, but they weren't originally designed for that. They're originally designed as kind of boundary conditions for climate models, and this kind of real detailed forest management practices aren't really included in them at the moment. However, this is starting to change. For example, the Jules Red model, which is using add trees, but not in GCB. So this is the model that's using the global carbon budget. This is the Triffid submodel of Jules. So this is how the vegetation competes in Jules. So you basically have average plants. So you might have 5 different types of tree, and they compete for space. You know, some prefer drier, some prefer warmer, whatever it is. And then they just compete and outcompete each other. And you have an average PFT. So it doesn't really have any age structure, and it doesn't really capture mixed stands very well. On the flip side, you have Jules Red, which is Arthur's model, which basically has this explicit age characterization, which you can really then start to see realistic kind of mixed stands, which is why it's so important. And this is kind of the key development for add trees and net zero plus and all these kind of plantation exercises. Is Triffid on the left couldn't do it; it grows way too slow. Jules Red can. So this is kind of the key aspect. Okay, so that was a kind of very quick overview of the carbon cycle, a big picture, and then just zooming into kind of what's the potential climate risk to the UK carbon cycle. So I looked at the climate change risk assessment, which was produced last year, I think for the UK government, I'm not too sure, but I looked at the land use sector, and there's these 4 kind of key bullet points. They kind of, what are the major risks? And basically, the climate impact on soils. So as we get warmer and drier, what's the impact on soils going to be? Then you've got the long-term response of temperature and water changes to natural carbon stores, and then forestry production, extreme events, including fire, wind, and then pests and pathogens. I'm going to leave pests and pathogens to Jonathan and Dan, and I'm going to talk a little bit about the top 3. So soils. So I've plotted here, again, this is Jules' output, so whether this is realistic or not is a different question, but Jules suggests that over time, over the last 100 plus years, we've had a loss of soil carbon in the UK, pretty much everywhere, apart from kind of a bit in the east. And this is likely driven by increases in temperature. So as we increase temperatures over time, we increase heterotrophic respiration, so the Q10 function in Jules. As you increase temps, you increase the respiration rate, and we have losses of soil carbon. And this is something I haven't really seen much of in kind of add trees yet, is how we address soil carbon. We've seen a lot on vegetation and a lot on MPP, but I think we really need to start thinking about impacts on soil carbon as well as just vegetation, to really look at what the net effect is going to be. Or maybe it has been, and I've just missed it. Okay, so now, not just thinking about soil carbon, but thinking about kind of the net sink in total. So this is biomass plus the soil carbon change. I thought I just wanted to kind of understand how the UK's kind of carbon sinks actually respond to climate change and climate variability. So I plotted the model output of the net carbon sink against different climate variables, basically. So here I've got net carbon uptake, some positive values indicate increase in carbon into the land, and then the negative values are losses of carbon against soil moisture. And basically, you have this strong negative correlation indicating that higher soil moisture, you actually get a reduction in carbon uptake, which is a bit kind of confusing because you think when plants like water. But this is because I haven't controlled for the fact that when it's wetter, it's because it's rained more. When it's rained more, it's because it's cloudier. When it's cloudier, there's less sunlight. And if you plot the same kind of net carbon uptake against solar radiation, you actually see this kind of high positive correlation. So actually, it's radiation that's kind of dictating the UK's carbon cycle, not necessarily soil moisture at the moment. We're not really water limited in the UK now. The future we might be, but it's really kind of we're energy limited in the UK. And then again, the same thing against temperature, and you don't really see much of a pattern. Not saying it's not important, but it's maybe not first order. So yeah, so kind of historically, I'd argue that the UK is energy limited, not water limited. However, this could change in the future. When we're getting drier, we could have a kind of, this could switch and we could have a tipping point. And especially when we have extremes, we could have extreme droughts, extreme fires, and this relationship might not necessarily hold. And I think linking back to kind of add trees is, at the moment, Jules has quite a simple formula relating soil moisture to carbon uptake. So you have Jules calculates the soil moisture, and then you have a simple ramp function, which the drier it is, you kind of have this ramp function which then decreases photosynthesis in the model. But there's no actual explicit representation of mortality or drought mortality, which could happen in reality. So you could have, for example, in drought conditions, you could have embolism in the tree. That could actually kill the tree off, but we don't have any representation of that at the moment, although it's being worked on right now in our group in Exeter. When it's into Jules is a different question, but this is being currently kind of researched. One thing which wasn't mentioned in the CCRA report, or I didn't see it, was ozone. So ozone is kind of basically, surface ozone is a function of NOx. So nitrous oxide is produced by pollution, VOC, sunlight and temperature. And if you look at the kind of maps on the bottom, this is kind of ozone concentration. So on the left is kind of where we are now, which is kind of, green is not that much of an issue. But as I said, because ozone is a function of those things on the top, as we have more trees produce VOC. So these volatile compounds kind of emitted out of the leaves. As we plant more trees, we're going to have more VOCs. As we have climate change, we're going to have higher temps, which are both going to increase ozone concentrations. And ozone, as you can see on the top right, can just damage leaves. And there was a paper from Stephen Sitch a few years ago, which this could have up to reduction in basically photosynthesis by up to 30% in a kind of high sensitivity scenario. Jules can do this, so we could turn ozone damage on in Jules if we want to, and we could find some ozone fields and feed this through Jules and see what would happen. So this is something we could look at if we wanted to explore this further. Fire. So this is one which I keep kind of flitting my head, is it important or not? Because I spend a lot of time thinking about global scale processes, and obviously fire in Africa and South America is a lot more important in the UK. But as you can see, so this is fire emissions from Jules Inferno. So this is the model of Jules I run. So it's the one not with Reading. And this is the fire emissions over time. And you can see actually we're having much more fire in recent years driven by increased temperature basically. But also we're having much more extremes, and it's these extreme events which are really going to cause damage to ecosystems. So looking at this plot, I was kind of like semi-convinced actually we really need to start thinking about fire more.
Mike, what's the unit of this?
On the fire,
Yeah.
Teragrams of carbon per year. So if I go back to what the UK carbon budget was, where is it? Here. So this is teragrams of carbon per year as well. So it's basically what the carbon sink is. You could argue, so that a lot of countries don't include fire emissions in their reporting because they have the argument, oh, okay, we're going to have a fire, but it's going to regrow. So over a long period, on a long time period, we don't need to account for fire because it's just a natural state. The question is, how is climate change going to impact that, and are you going to have regrowth? So I would argue you probably do need to include fire. This is just the fire weather index that I saw in a paper that's been published recently in the UK over time, and you can see the current state. I don't know what the actual unit is, but it's a percentage of days exceeding probably some threshold. And you can see under probably a 2-degree warming, which is probably where we're going to be heading, we can see in the southeast we're going to have a much, much higher incidence of fire weather. So in terms of add trees, we've got two options. We could try and include this fire weather index directly into the tool and talk about fire risk, or we could wait till March. And I spoke to Arthur recently, who's the lead developer on Jules Red, and he promised that by March next year, Jules Red would have fire embedded in it. And I'm not sure exactly what the timescales for the tool or the project is and stuff, but whether we could, hopefully by March next year, we could then start running Jules Red with this fire mortality included. Okay, so the last thing I want to talk about is wind damage. So this is something which isn't included in Jules at all. And luckily, Forest Research have got this off-the-shelf model ready built, ready to go, called Forest Gales, which basically you feed in information of the tree type or the stand type, the species, the height, the diameter of the tree, the rooting profile, the gaps between trees, spacing of the plantation, loads of different parameters. And it calculates, using various moments and physics, and I can't remember exactly what it is, but it basically calculates a critical wind speed. So it says, okay, given your stand and all the properties it entails, if wind hits this value, you're going to be damaged. But if it hits this value, you're going to be overturned, or this damage, So given a wind speed distribution, so the key drivers of the model, so they've done sensitivity analysis on what are the key parameters, and it's basically tree height and diameter. So as you get taller and taller trees, the force on the tree when the wind hits it is greater. But obviously, as you higher, bigger diameter, the tree's stronger and it can withstand that force. There's also spacing, so the spacing between the trees, and then the gap size. So if there's gaps here, this is basically the bending moment. So this is the force applied on the trees, and you can see it closer to gaps, you have a higher bending moment. So this is a parameterization in the model. So I just started playing with it, basically. I just selected a spruce plantation, and I just selected kind of semi-random input variables. I said, okay, we've got a height of 30 meters, a diameter of 15 centimeters. I've no idea if spruce actually grows like that or not. A spacing of 2.5 meters, and then I just kind of kept some random parameters for the other things, and that seems sensible. And it spat out these numbers. I said, if you hit 13 meters per second, you'll be damaged, and if you hit 21 meters per second, you'll overturn. Okay, great. However, it's gusts that cause the most damage, or can cause the most damage, but they only last for a few seconds. And the wind data we have is often hourly. So what the model does, it represents wind speeds with this kind of Weibull distribution here. So, and it's really the tails of the distribution which dictate the probability of damage. So for example, you can have two different wind states here. So the black line is, well, the kind of x-axis is wind speed, and this is the PDF. And you've got the black curve is a low wind, low variability state, and then the red curve is a high wind, high variability state. And what you can do is just fit this. So you give it some wind data, and you can fit these parameters and feed those parameters into the model, and then it'll spit out a probability of damage or overturning. So you've got one parameter controlling the mean and the other variance. And I was just interested to see what the sensitivity of this model is. So again, I just plotted the scale parameter on the x-axis, which is basically mean wind speed, and then the variability on the y-axis. So as you go up in the y-axis, you basically get lower variability, and then the shading is the probability of damage on the left and probability of overturning on the right. And you can see, so basically in the top left, where you've got no probability of damage, is where you have low wind, low variability, and then when you have basically 100% chance of damage, is where you have high wind, high variability on the bottom right. So what I did is basically looked at a quick case study. So I took Dartmoor, downloaded the Era 5 wind data, which is 10 kilometers for Dartmoor. And then I think it's hourly. And I chose 2021 because there was a massive storm that came through in November, which caused destruction across the country. And I thought, okay, what would this look like in forest scales? And I thought, okay, so I'm going to put that spruce plantation on Dartmoor and see what happens, basically. And you can see this is the wind speeds here. So the black line, I think, is just the daily mean speeds, and then the red is kind of the weekly. And you see there's various peaks here. So I think this is a major storm that came through, but there's also kind of peaks throughout the year as well. So yeah, so I took the data. So every 12 hours, I fit the data to the distribution to basically give the parameters into forest scales, which then calculate the probability of damage and overturning. Okay, so you've got probability of damage on the y-axis, you've got time on the x-axis, and I've got two plots. So I basically did it for two different heights. So on the left is you've got a 16 meter stand, and then the right is a 30 meter stand. And you can see for the shorter stand, obviously the force on the tree was lower, so there's basically no damage. But on its higher stand, you can see these spikes of damage where you basically have 100% probability of damage. But I think this is probably because I chose these thin, tall trees, you know. So it's kind of, but yeah, you get the idea anyway. And then you can do the same thing for overturning. So obviously, so there's a high probability of damage, but not death. And then if you had these trees actually on Dartmoor, when that Storm Harwin came through, that massive storm that came through in 2020, end of 2021, you'd basically, what is that, like a 40% chance of flattening the forest. I've got lots of questions about this because I've been playing around with it. I think I need to speak to someone at Forest Research about how to use this model and how to actually, best use it for our scenarios and actually understand what I'm doing, basically. But it was quite easy to use. You know, you could download it. It's an R package. I just started plugging in variables and started just making nice little plots, and it was pretty cool. And then speak to Arthur as well, because obviously he's the lead developer for Jules Red. Yeah. He's the lead developer of Jules Red, and he'd know best about how to integrate this into Jules. And this is kind of the overview of Jules Red. So it's basically the number of trees plus the kind of mass of trees is balanced with the mortality of trees. So this is kind of the mortality parameter here. So this, whatever Greek letter that is, lambda, no? Gamma, thanks. I did a maths group, so. So yeah, and then it's pretty simple in Jules to just plug in whatever mortality parameters you want. So in March, we can hopefully get the fire one. If we kind of continue working on this wind one, we can then start plugging in a wind mortality. Simon's working on drought next to, we can then start plugging in the drought mortality. And then hopefully, because at the moment we've got in Jules Red this kind of like background mortality rate, which captures all the mortality, and we can slowly start to reduce this background mortality and add in more of our mechanistic mortality is the kind of plan ideal. Last thing, this is nothing to do with the talk, but I thought, what does Gaussian process emulators, statisticians in the room? I think there's further opportunities for collaboration across kind of the communities, especially in the carbon cycle world. We struggle with a lot of things, which I think you could help with, especially with like using our models. Jules takes an age to spin up the soil column because the turnover is so slow. So I was thinking maybe we could emulate soil carbon and. Okay, I'm getting looks. I'd like to talk to people more about how we could basically work more on integrating the communities and kind of improving carbon cycle modelling. And that's it. I'll stop there.
Think of talking.